This is your first set. And with one sample hypothesis test, we got one of three categories. The first category, which is the last one we'll do today, involves a sample proportion. We don't have to worry about the standard deviation because, as you'll recall, the standard deviation for a proportion comes from the proportion itself. The rest has to do with sample means. Now, with sample means, we have one of two possibilities. We have the population standard deviation, or we have the sample standard deviation. If we only have the sample standard deviation, then we don't know the population standard deviation. That means we'll have to use the t distribution. Whereas if we know the population standard deviation, then we can use the normal distribution. So those are our three categories. We're going to start with the easiest one. And this one is if we're dealing with the population mean and we know the population standard deviation. We'll use our sample mean as our point estimator. Now, when we do our hypotheses tests, you have one of two possibilities. It can be one-tailed or two-tailed. If you don't recall what that means from the previous one, let's say we have our null hypothesis, and our null hypothesis is that we're equal to some value mu naught. This mu naught, by the way, is what that mu naught stands for. Mu naught is the value from the null hypothesis. Then therefore, everything else is not equal to mu naught. In this case, we could be not equal to in one of two directions. If we're down here, not equal to. If we're up here, it's not equal to. So in this case, it can come in one of two tails. And so we have to consider both possibilities. On the other hand, let's say we're dealing with less than or equal to. In this case, whether or not, well, if we're anywhere in here, the null is fine. On the other hand, if we're up here, it's not. So we only have to worry about one tail, and that's why it's called one tail. Now, whether or not we have one tail or two tail, the process starts out the same way. The first thing you got to do, you got to make sure you have your sample mean and your population standard deviation. So if you want, and I'll type it out for you, requirements. That's not how you spell it. Requirements. We have a sample mean, and we have the population standard deviation. You satisfy both of those, then we get to use this. Now, if our test, whether or not it's one-tailed or two-tailed, we get our test statistic. And you'll recall the test statistic, we can do one of two things, well, three things technically. We can do a confidence interval, but we're primarily going to focus on the other two methods because we've already covered confidence intervals. One thing is we can convert this test statistic into a p-value. The other way is we can convert our alpha into a critical value. Either way, you're going to do a comparison, but no matter what, you start out the same way. You have to get your test statistic. You'll recall this z-score formula, you've seen this already. This was from chapter 8. The only difference is we've changed the definition of it, well, like the name of it, technically speaking. Now, let's suppose we're dealing with our one-tailed one. In this case, our p-value is equal to the probability of a z-score being less than the negative of the absolute value. You might say, what is the point of that? Why can't I just say the probability? For example, in this one tail, you might ask, why can't I just get this probability? You can do that. That'd be absolutely correct. Here's the catch. Let's say you go into your table and you get the p-value associated with, say, z being 2.5. That's the probability of being below that value. You need to get above. So you'd have to use the complement law. And I know the most common mistake, both on the assessment number 2 and on the midterm exam number 1, was incorrect use of the complement law. So the reason why I'm including this absolute value bar along with the negative sign is so that you get to completely ignore the complement law. Because here's how it works. Let's say we have that 2.5. Absolute value of that's still 2.5. The negative makes it negative 2.5. So that'll give you this probability. But because the normal distribution is symmetric, that's going to be the same as this probability. So therefore, all you have to do, absolute value in the negative, take care of the complement law for you. Now, a quick question you might ask is, why can't I just take the negative? Because if you have the negative z-score, you just made it positive, you're going to screw up. So taking the absolute value makes it positive. Throwing on the negative guarantees it's negative. What that also means is you do not need, for the tables, you don't need the positive values. You only need the negatives. And in fact, you'll see down here, in all of these examples, we're only going to use the negatives. We don't need the positives. So that's how you get the p-value. If you're doing the p-value approach, all you do is compare that p-value to your alpha. If it's less than, reject. Otherwise, fail to reject. The other approach is the critical value approach. With this one, this is basically working backwards from your alpha. So you're going to want to find the z-score where the p-value is equal to alpha. So for example, let's say our alpha was 0.05. In this case, we would look for 0.05, and that's going to be somewhere in between here. So negative 1.645, something like that. And so our critical value would be negative 1.645. Now keep in mind, if your alternative hypothesis has the greater than symbol, then that means you're over here. So that means your critical value needs to be positive. So the one thing you have to keep in mind, if you have the greater than symbol in your alternative, then you're going to have to take the absolute value of that critical value and make it positive. For two-tailed, it's very similar. You still get your p-value from the p of z being less than the negative of the absolute value. And as a note, these right here, that's not two negative signs, that's one negative sign. So if you see these two little minus signs, that's one negative sign. I didn't want to use just one to be very small, it might be hard to see. The difference is now we have to multiply our p-value by 2. You might ask why? Well, the boring explanation is two tails, so 2. But the reason why is so we get this p-value right here. But the thing is, we also could have been over here. And because it's symmetric, the probability of being in the upper end is the same as the lower end. So we got to multiply by 2 to account for the fact that we could be on both sides of it. Okay? And the critical value, the only difference is instead of setting it for alpha, we do alpha over 2. The reason why we do alpha over 2 is because alpha over 2 times 2 gives us alpha. So we're canceling out for the 2. So let's say we had 5% as our alpha. That's 0.05. We divide that by 2, 0.025. Oh, what's this? Out of the way. So we go down here. Let's look for 0.025. That is going to be right there. So negative 1.96. So again, working backwards. So before I continue, does anyone need more time to write this down or take a picture of it? Okay. I'm going to work through 2 examples, and then you'll do the third one on your own. And all of these examples, with the exception of the one for proportions, are going to come from web. So let's suppose we have this hypothesis, our mu is 940 or greater than 940. Right? Ask, hold on, why isn't it less than or equal to 940? There's no difference as a practical matter. We will interchangeably use both. When you get on the job, we recall we set up our hypotheses in one of 2 ways. We either want to challenge our assumption, and we recall the null is the assumption, or we have some sort of idea that goes against the conventional wisdom, and we want to prove that our idea is true. If we have this idea, since the null always has the equal, that means our alternative is either going to be less than or greater than. Well, let's say we think our alternative is greater than, then we have some sort of reason to justify it being greater than. And if we have some evidence that's already suggesting that, then it's pretty reasonable to assume that we're not going to be less than, so we don't have to worry about it. And in fact, you'll see when we're doing these hypotheses tests, whether or not it says mu is equal to 940 or mu is less than or equal to 940, doesn't really matter. You can use them interchangeably. When you're actually on the job and doing research or just stuff for your business, this is usually how you do it. So we have a sigma of 230 at end of 100 and X bar of 988.3 and our alpha is 0.01. Don't worry about drawing the sample distribution. So first of all, we know the population standard deviation, that's 230, and we have the sample mean of 988.3. This means we can use this. So first we need our test statistic. We recall our test statistic is equal to X bar, so 988.3, minus our hypothesized population mean, which is 940. And then we divide this by our population standard deviation over the square root of our sample size. The population standard deviation is 230. And our sample size is 100. So just to simplify it before I put it in the calculator, if you want, you can go straight to the critical value, the test statistic at this point, because that's just throwing it into a calculator. I'll just do a quick little bit of mental math to make it a bit easier. 988.3 minus 940, that is 48.3. Square root of 100 is 10. 230 over 10 is 23. And now I'll pull up the calculator. Let me share the entire screen for those of you over Zoom. There we go. 48.3 over 23, exactly 2.1. That's nice. So our Z score is 2.1. So I'm going to skip part B for a moment. Let's do part C and get our p-value. We'll then do part D, and then we'll go back to B. So our p-value, we recall our p-value is equal to the probability of Z being less than the negative of the absolute value. So negative absolute value of Z, negative absolute value of 2.1 is negative 2.1. So let's look in our table. There's 2.1. There's no decimal beyond that. So 0, 0. So this is our p-value. So our p-value is 0.0179. So now we will reject if this p-value is less than alpha. Our alpha is 0.01. We can't reject. We got really close. If this alpha was 0.05, then we would have rejected. But this 0.0179, it's not quite there. So in this case, we do not reject the null. As a note, you never reject the alternative. You never fail to reject the alternative. So if you see anything involving H1, it is instantly wrong, because we only make decisions involving the null itself. Now let's go back to this rejection region, right? That's what's rejection region. The first thing we got to do is get our critical value. So let's get the critical value. We recall the critical value is the value of alpha, or is basically the Z-score that satisfies one of these two. Which one do we use? Well, here we have greater than. This means we're only dealing with one end of the tail, so it is one-tailed. As a note, if it had said mu is not equal to 940, then we'd have two-tailed and use the alpha over 2 formula. So in this case, we have alpha is equal to P of Z being less than the critical value. So our alpha is 0.01, and this needs to be equal to the Z value. I'll just call it crit. So we go to our table. We want to find 0.01. That is somewhere in between these two. Looks like it's going to be closer to 0.03, but regardless, we will say that this Z value is approximately Z is equal to negative. Oh, here we go. Negative 2.326, something along those lines. In web work, you'll have to be careful of rounding there. If you are not 100% sure of that, you can always use the Z confidence tables, because the Z confidence tables, you'll recall, give you the 3 decimal places. With here, I'm using this, so you can get used to the concept of it. Now, as a note, we recall from the one tail, if our alternative hypothesis has the greater than symbol, then we have to take the positive. In this case, we have the greater than, so we have to take the positive. So in this case, our critical value is 2.326. And therefore, you can even clearly see our test statistic is not greater than that critical value. Now, for the rejection region, If our z-score is negative, we're obviously not rejecting because the only thing we care about is if it's too high. So our lower end is going to be 2.326, and obviously we can go up to infinity, so that'll be our rejection region. If we were dealing with two-tailed, you'd also have to include the lower end. So before I continue to the next example, are there any questions about this process that I have used here? And just to give you an interpretation, because I'll ask you to interpret these things, an interpretation of this hypothesis test is that we would say we failed to reject the null hypothesis that mu is equal to 940. Now, just as a bit of recall, you'll recall that a type 1 error is a false positive. So in this case, a type 1 error would be rejecting the null hypothesis that mu is 940, when in fact, we shouldn't have rejected that. And you'll recall type 2 is a false negative, so that would be failing to reject when we should have. Anyways, let's go to our next one. And by the way, I don't think we're going to get anywhere close to the full lecture time, which is good because we've been taking it a little bit slower, as many of you requested. So let's go with our next one, 920 and 920. Like with before, we have our standard deviation of 160, and we know it. That's our population standard deviation. And we have our sample mean. So therefore, we will be able to use our formula from up here. Let me scroll up just a little bit so you can see the whole thing. So in this case, we start the same as before. We need to get our test statistic. So Z is equal to our X bar, which is 944, minus 920, divided by our standard deviation, which is 160, over the square root of our sample size, 85. And here, we'll pull up our calculator. So the numerator is 24. We divide by 160, that's 0.15. If we're dividing by a denominator in the square root, that's the same as bringing it up to the numerator. So we have the square root of 85 and times the 0.15. So our z-score, we'll call that 1.383. And note, it's okay to round this here because when we use our z-tables, it's rounded off to 2 decimal places anyways. When you put this test statistic in the web work, you're going to want to round to 3. Now, we're going to go to C. We want our p-value. So we have to take the negative of the absolute value. So negative 1.383 is the z-score we'll use. So negative 1.3. And then we need the 0.08, which is a little bit off to the right. That's right there. So p-value is equal to 0.0838. And in this case, our p-value is not below alpha. So therefore, we fail to reject the null hypothesis. And again, B and D are nonsense because we never, B and D, A and B are nonsense because they deal with the alternative. We never reject or fail to reject the alternative. We either fail to reject the null or accept the alternative. Because if we reject the null, then we're accepting the alternative. Now our rejection region, as a note, again, like if this alpha was 0.1, we would have rejected. So you might ask, hold on, can't we manipulate hypothesis tests by determining our alpha after we're done? Hypothetically, yes, but it's good practice for hypothesis tests that you determine your value of alpha before you actually do it. I will always give you the value of alpha or the confidence level. So I give you the confidence level, just 1 minus that, you get your alpha, but you'll always have your alpha beforehand. Sometimes you'll have to pick it yourself. You won't have to pick it in this class, but sometimes when you're on the job or doing research, you'll have to pick your value of alpha. And generally the value of alpha you pick is how willing you are to tolerate a screw up. If you're dealing with calling elections, that screw up cannot be high, because if that screw up is 5%, there's a pretty good chance between all those states you're going to screw up and call one of them incorrectly. So that's why, the networks, they will do alphas of like 99.9% confidence. And when you do your practice midterm exam and the actual midterm exam, you'll deal with the confidence level that low. Anyways, so now for our rejection region, we need the critical value. Again, this is one-tailed because we have greater than. So we have 0.05 is equal to P of our Z value being less than the critical. So we look for 0.05. It's going to be right in between here. We'll take the halfway point. And we'll call that negative 1.645. That is actually the correct value. But we're not done yet. First of all, we got to take the absolute value of that. And the reason why is since we have the greater than symbol, we're in the upper tail. So we got to take the absolute value of that. And now any critical value above that will lead us to reject it. Because if we get a critical value above that, then we'll get a p-value below 0.05. So we'd have 1.645 to infinity. Let me make that more clearly a dot. So the 1.645, our alpha is equal to the probability of Z being less than the critical value. We're trying to find the critical value that satisfies this equation. So we have to work backwards. We have to find 0.05 in the table. It's 0.05 is in between these two. So we split the difference and we say that it's right here. Right there, we have negative 1.6 and halfway between 0.04 and 0.05, so negative 1.645. Now, the reason why we have the positive is because since we're dealing with the greater than symbol, we're in the upper tail, and the upper tail of a normal distribution always has positive z-scores. Therefore, we have to make this positive. Does that help, Braden? All right. I'll give you one to do on your own. I'll give you a couple of minutes to work on it, and then we'll go over the answer. So here, I'm going to move this table a little bit to the left so you can see it better. There we go. Now, come on. Let's go a little bit further. There we go. All right, I'll give you a couple minutes to work on this. And I really strongly recommend you work that out on paper, or I guess on your iPad or at home. Correct. If you use this approach up here, where our p-value comes from the negative of the absolute value, you don't have to worry about the complement law, and you don't have to worry about the positive end of the Z and T tables. So I recommend having the negative Z and T tables. I also recommend printing out the Z confidence table, because sometimes that'll give you the shortcuts. Because if you're dealing with two-tailed, it'll give you the shortcut pretty quickly. All right, so I'll give you until 6:30 to do this one, and then we'll go over the answer. All right, I'll give you an extra minute and then we'll go over it. All right, does anyone need more time? So see a couple of you writing. I'll give you maybe an extra 15, 30 seconds. All right, let's go over the answers. So we start off with our test statistic. Whether or not it's one tail, true tail, doesn't matter. Test statistic always starts out the same way. We have our X bar, which is 1135, minus our mu naught, which is 1090. And we divide by our standard deviation of 250 over the square root of 85. We pull up the calculator. Square root of 85, same as bringing that in the denominator. 1135 minus 1090 is 45. And divide that by 250. And we get a z-score of 1.660. Now we're going to skip B. We're going to go to the p-value next. So our p-value, we have to take the negative of this. So the negative of the absolute value is negative 1.660. You'll note with all of these, I have dealt with alternatives or were greater than. And the reason why is so you get used to doing the negative absolute value. So this p-value, we're dealing with one-tailed again. So in this case, we're looking for negative 1.66. Here's our negative 1.6. There's the 0.066. Bring them together. And our p-value is 0.0485. I just recommend going out to 4 decimals in the web work because why not? If you have an exact answer, put in the exact answer. So now our alpha is 0.05. This p-value is less than the alpha. Therefore, this time around, we're going to reject. And let's verify that through our critical value. Again, since this is one-tailed, we're going to have our value of alpha. So 0.05 needs to be equal to p of z being less than our critical. So we look for 0.05. Like before, the 0.05 was right here. So the halfway point was negative 1.645. But we got to absolute value that because we have the greater than symbol. You'll notice the greater than symbol is generally the one that gives you extra troubles because that's the one where you always got to keep track of your signs along with the absolutes and negatives. So that's why I've been focusing on greater than signs, because if it's less than, you got less steps, quite literally. So we take the absolute value and our critical value is 1.645. So our rejection region is 1.645 to infinity. And therefore we can very clearly see our test statistic is inside that region. For the exam, you'll be using the p-value approach because that one is generally more reliable and is less likely to produce a mistake. Now, let us suppose, just for the sake of argument, that this was a two-tailed test. Yes, correct. If the p-value is less than alpha, we reject. Otherwise, we fail to reject. If you're still a little bit unsure about some of those concepts, you can always rewatch the chapter 9A lecture. I think that one was around 40 to 50 minutes. So not too long. So let's suppose this was two-tailed. So let's suppose it was not equal to. Well, if it's not equal to, the z value is still the same. The difference, and this p-value we got is still nearly the same. We recall if it's two-tailed, the only difference is now we have to double the p-value. So if it was two-tailed, then our p would be equal to 2 times 0.0485, which I believe is 0.097. Let me minimize that. So if it was two-tailed, we would have failed to reject. This is another reason why, say, going with equal and then greater than and not including the less than is good. Because if you have a prior that gives you an indication of what your null might be, it makes it more likely that you don't screw up. And likewise, the critical value, we would have 0.0025 is equal to p of z is less than crit. So in this case, the 0.025, where is that? 0.025 was right there, so negative 1.96. So then in this case, we'd go from both directions. So in this case, if we had two-tailed, we would have been negative infinity to negative 1.96, and then 1.96 to infinity. But that's only if it was two-tailed. Again, you'll notice two-tailed, you technically have the extra step of multiplying or dividing by 2, but it also means you never have to give a damn about the signs. Are there any questions about hypothesis tests for one sample standard deviation known? Okay, we're going to skip the standard deviation unknown for a moment. We're going to go to proportions. So here are our formulas for proportions. Test statistic is our p-var minus the p-naught. Again, p-naught comes from the null hypothesis. And you'll recall that square root numerator, or the denominator, you've seen that before. And again, you'll notice that our formulas for one-tail and two-tail, you don't need to write this down. All you have to do is write down the formula for the test statistic and then literally draw arrows for your two formulas for one and two-tail that you wrote for your z-scores. Because you'll notice they're the exact same. The reason why they're the exact same is because the population proportions also use the normal distribution. So all you got to write down is that first box and then draw arrows from one-tailed to two-tailed to that box as well. So if you want, you could have, say, your one-tailed right here, your two-tailed here, and then say you could have test statistic. This is very messy. I'm writing too fast. Test statistic for standard deviation known, and then for proportion. And if you want, on your cheat sheet, you can do it like this. It'll save you some space. Whichever way you prefer. So I'll give you a moment to write this down, and then we'll go into the examples. All the remaining concepts are the same. Like with one tail, we only can care about the upper end or the lower end. So if we're dealing with p is greater than, then we're in the upper end. You got to worry a lot about the signs. If we're in the lower end, no big deal. And you'll notice most of the examples we do are going to be the upper end because that's where you're more likely to screw up. If you can handle the upper end, you should be able to handle the lower end. If you're at home, I recommend you use the snipping tool. If you don't know how to find it, pull up the search bar and type in snipping tool. So you can just snip that. And those of you who are here in person, you can take a picture. But again, I just recommend writing this one, the box down, because the other ones you can just draw arrows, save yourself some time. Does anyone at home need more time to write this down or take a picture of it? I know our people in person are good to go. Okay, I'll give you about a minute to write it down. And again, you don't need to write down one tail, two tail, just draw the arrows. Save yourself some time. All right, James, you good to go? All right, let's go to our examples. We have this poll sample size of 1,000. We're testing gay marriage. All we have is a sample size and the proportion that support gay marriage. So now we're going to conduct the hypothesis test. We have to make the hypotheses, and we got to find our alpha. So our first thing since we're trying to see if it's greater than 2/3, in that case, our alternative is that our P is greater than 2/3. We'll just quite literally do 2/3, so 0.667. I'm just going to round to 3. The null, you can do one of two things. On the exam, what I will do is I will specify the signs for you. So all you'll have to do is figure out the values. In this case, we'll just go with the opposite. So less than or equal to 0.667. Our alpha is equal to 1 minus our rho. Our rho is our confidence. So 1 minus 0.95. So 0.05. Now we have what we had before. We can get started. Our test statistic is equal to our P bar minus our hypothesized P naught. Our P bar is 70%, so 0.7. Our P naught is 0.667. And now, remember, we can divide the square root. We can apply it to both. So here it's P naught times 1 minus P naught. So here we have 0.667 times 1 minus 0.667. And then we divide by the square root of our sample size, which is 1,000. So the easy way to do this will be 0.667 times 0.333. We will square root that. That is our denominator. Remember, we can bring the square root of 1,000 up. I should have done that first. Whatever. Let's pull up a second calculator. This one is where it's better to use Desmos. So let's just go up to Desmos. Let's make it easier. Generally speaking, Desmos will make things much easier. 0.7. Yes. 0.67 minus 0.667. Square root. Our sample size is 1,000. 0.667 times 1 minus 0.667. And so we get our z-score of 2.214. So for here, I was about to get to that. This is one-tailed because basically here's the very easy way to figure out if it's one-tailed or two-tailed. If the alternative says not equal to, two-tailed. Otherwise, one-tailed. That's your nice and easy shortcut. And you'll recall for our test statistic, we never have to worry about sign. Whatever it gives us is whatever it gives us. Now, it says to use the p-value approach. So in this case, we take the negative of the absolute value. So where's my mouse? Negative absolute value of z is negative 2.214. So negative 2.1. Oh, no, I'm sorry, 2.2. Sorry. Negative 2.2 and the 0.01. That is going to be, so our p-value is equal to 0.0136. Finally, we compare this to alpha. Since the p-value of 0.0136 is less than our alpha of 0.05, we reject the null hypothesis that less than or equal of 2/3 of Americans support gay marriage. Let's make this bigger. Hence, And so therefore, if we reject the null, we're accepting the alternative. So hence, we can say that more than 2/3 of Americans support gay marriage. And this, by the way, was an actual Gallup poll. Any questions before I move on to the next example? Okay. Next example, now we're going to go back to Georgia. So 2022 Senate election, Raphael Warnock's up for again. We have a poll, 51%, sample size 499. We want to test the hypothesis that he and his Republican opponent are equal in terms of vote share. So we're going to do a hypothesis test at 99% confidence level. You'll notice this is much higher confidence because, again, this is the type of race you don't want to call incorrectly because there's a very good chance it might decide control of the Senate. So here we have our H naught and our HA. We identify H naught first. And the reason why is because we are testing the hypothesis. So we're challenging the assumption that they have an equal vote share. So therefore, their two P's are the same, which means they're both 50%. The alternate is the opposite. So we have P is not equal to 0.5. You'll immediately notice this means we're going to be having a two-tailed now. And that intuitively makes sense because with two-tailed, it could be him winning or it could be his opponent winning. Doesn't matter who, as long as someone's winning. So our alpha is equal to 1 minus rho. So our confidence is 99%. So our alpha is 0.01. On the exam, you're going to start out the same way. And in fact, what I'm doing here is really pretty much the same process, but you'll have different numbers and perhaps a different type of hypothesis test. You're going to have to identify your hypotheses. You'll have to identify your alpha. You'll then identify your test statistic, and then you'll reach a conclusion. So let's get our test statistic next. This is equal to our P bar, so 0.51, minus our hypothesis size, so 0.5, divided by our two square roots. And again, you can make it all one big square root, doesn't matter which. 499, and now we have 0.5 times 1 minus 0.5. Oh, that should be, sorry about that, let me make that clear. A common mistake people will make is instead of putting 0.5 in the denominator, they'll put 0.51. What you put in the denominator has to be what you get from the null, not from the sample. So let's switch over to Desmos and put that in there. So 0.51 minus 0.05, I'm sorry, 0.5. And then we have the square root. Sample mean goes in the denominator, or denominator of the denominator. Then we have 0.5 times 1 minus 0.5. So we get a z-score of 0.4467. We'll round that, 0.447. So now our p-value. We start off the same way, take the negative of the absolute value. So we have negative 0.447. So negative 0.4. That 7 will knock that 4 up to a 5. So we look for the 0.05. So we get this p-value. If you enter that p-value, you get it wrong. Because our p-value is double that. Because it's two-tailed. So we have to double this 0.3264. And so we get 0.6528. So, and I'll just draw the arrow, times 2 because two-tailed. In this case, this p-value is nowhere remotely close to the confidence level. But even with a p-value this high, we do not accept the null. We just simply say we failed to reject it. Since p-value of 0.6528 is well above the alpha of 0.01. If you just say above or you say well above, those are both still correct. I'm not going to be nitpicky there. On the other hand, with your correlations, you can't just say strong, you might have to say positive and strong. So a bit of a distinction there. we fail to reject the null hypothesis that Georgia's 2022 Senate race will be a battleground. You'll notice that also puts it into context. When I ask you to give your conclusion, you're going to have to put it into context. Putting it into context is really just saying we failed to reject the null, which is we failed to reject the null hypothesis that blah, and you state the null in English. Because really, this right here, 2022 Senate race will be a battleground, that's just saying P equals 0.5, but in English. Okay? I will now give you a couple of minutes. Do this one on your own. And at 53, we will go over the answers. Then we'll move over to our last one sample category of hypothesis tests. All right, does anyone need more time? All right, let's go over the answers. So first, we got to get our two hypotheses. So 4 or higher means greater than or equal to 4. However, it's asking if a majority think that. A majority is greater than 50%. The equal sign has to be with H naught. So therefore, our HA is that P is greater than 0.5. So therefore, our H naught is the opposite. P is less than or equal to 0.05. Our alpha is equal to 1 minus rho. So 1 minus 0.9, which is 0.1. So now our test statistic is equal to our P bar, in this case 56%, minus the hypothesized one, so 0.5. We divide it by square root of 0.5 times 1 minus 0.5 over the square root, let me make that clearer, of our sample size of 111. Let's put that into our calculator. 0.56 minus 0.5 for the square root of 1 So we have a z-score of 1.264. So the absolute value or the negative absolute value is negative 1.264. Since this is one-tailed, we just look it up in the table. We don't have to worry about doubling. So we look for negative 1.2. And now we look for the 0.06, which is right here. Draw the arrows down. And we get 0.1038. That is very, very close, but not quite. So since our p-value of 0.1038 is not less than, and notice I'm using less than interchangeably with above, because not less than is the same as saying above. I'm using them interchangeably, pick whichever one you want. It's not less than our alpha of 0.1. We fail to reject the null hypothesis. So right there, that is your conclusion, and the interpretation is the remainder of this sentence. So we fail to reject the null hypothesis that less than or equal to half the class thought the difficulty level was a 4 or higher. So the first part is the conclusion, second part is the interpretation. Are there any questions about hypothesis tests for one sample proportions? Okay, let's move on to our last hypothesis category for one sample. And this is now when we come back to our very annoying t-distribution. And here, these formulas for one tail and two tail, they change. So you're gonna have to write these down. So if we're dealing with a sample mean, but now we don't know the population standard deviation, then that means we have the sample standard deviation. So our requirements, we have sample mean, and 2 have sample standard deviation. Because if you have the population standard deviation, you don't care what the sample standard deviation is. So you'll notice the difference, sample mean sample standard deviation versus sample mean population standard deviation. For the other one, I don't need to list the requirements because if it's a proportion, duh. So here we get the t-score. The only difference in the formulas is that now we have a t-score. In our denominator, we use the sample size. Oh, I'm sorry, the sample standard deviation instead of the population standard deviation. Now you might ask, what happened to the n-1 in the denominator? Well, we recall our n-1 is with our degrees of freedom, which is right here. So with our p-value, we still start out with the same way. We take the negative of the absolute value of our t-score, our test statistic. Now, though, we have to find the probability of our t-value being less than that negative of the test statistic. And you'll notice here, this means now you need degrees of freedom. You recall the degrees of freedom is n-1. And if we're doing the critical value, it's the t-score that satisfies alpha p of t is less than critical value. And I'll show you how to get that. And like before, if you have the greater than symbol, then you got to make that critical value positive. For two-tailed, same concept as with the other two tails where we double our p-value or take half of the alpha for the critical value. So I'll give you a minute to write this down or take a picture. And then we'll go and do our examples. And then we will be done. Does anyone need more time to write this down or take a picture? And I will note the notes have everything written down If you want, you can just print this out and include it on your cheat sheet. You'll have to scale it down, obviously, but this has everything written down. Okay, let's go to our examples. So we have 5 measurements, sample mean 8.5, sample standard deviation of 1.59. We have alpha of 0.05. Test the null hypothesis that the mean is 7 against the alternative that the mean is less than 7. So H naught is mean is equal to 7. HA is mean is less than 7. So we get our test statistic. This is equal to our sample mean of 8.5. I'm switching this to a greater than sign. Let's switch that to be greater than, just so it makes more sense. There we go. 8.5 minus 7. And now we have a sample standard deviation of 1.59. So 1.59 over the square root of 5. So let's put that into Desmos. 8.5 minus 7 over 1.59 over the square root of 5. And we get our test statistic of 2.109. So now we have to identify our degrees of freedom. Our degrees of freedom are sample size 5 minus 1, which is 4. Since it's one-tailed, we need to find the p-value associated with the negative of the absolute value of the t-score, so negative 2.109. So now we have 4 degrees of freedom. And here is where things get interesting. You don't see that t-score anywhere in this table. Here's how we do it here. We get our critical value. So here, we will use the critical value. So in this case, for our critical value, it's one-tailed. So we have an alpha of 0.05. That is our alpha. So our critical value is equal to 2.132. So if you like it in equation form, 0.05 is equal to P, T is less than critical. Notice that made it positive, and thankfully, we're on the upper end. So we can just leave that there, but keep your signs in mind with this. The t-tables can be tricky. So, that said, in this case, since our test statistic of 2.109 is not above the critical value of 2.132, we fail to reject the null hypothesis that our mean is equal to 7. With the t-scores, you'll usually use a test statistic approach. Technically, you can find the p-value from the test statistic. Now, in this case, here's what would happen. On the exam, let's say I asked you to use the p-value approach. What you would do is you would notice that your t-score is 2.109. So we can say our p-value, we have 4 degrees of freedom. It's somewhere in between these two. So we'd say our p-value is higher than 0.05, but less than 0.1. So therefore, since it's higher than 0.05 and less than 0.1, we would reject because it's not less than 0.05. So if you're asked for the p-value approach, you should have to find which of these values it's in between. But on the exam and on the web work, it won't ask you to specifically enter that p-value. Again, what you'll do, you'll get your test statistic, and then you'll go to the conclusion. And what I'll have you do, you'll identify your hypotheses, you'll identify your alpha, you'll then identify what distribution you're using. In this case, we use a t-distribution because we only have the sample standard deviation. For our other two cases, we use the normal distribution. From there, I'll ask you to calculate the test statistic and put that in, and then you'll reach your conclusion. So you'll never technically have to enter your p-value. So with the previous two categories, you can directly get the p-value. For this one, we get a range for it. Anyways, let's keep going. Now we have 8 measurements. So again, let's get our H0, and I'm going to flip this. So the mean is 8.3. The alternative, mean, is greater than 8.3. In this case, we should have alpha is equal to 0.05. Our degrees of freedom is our sample size of 8 minus 1, which is 7. Our test statistic is our sample mean of 9.9 minus our hypothesized mean of 8.3, divide by our sample standard deviation of 1.97 over the square root of our sample size, which is 8. So let's put that in here. I believe what did we say it was 9.9 minus 8.3. And then we had 1.97 over the square root of 8. So we have a test statistic of 2.297. So if you wanted to, negative absolute value of t would be negative 2.297. In this case, doesn't really matter because you're still getting the range. So now let's get our critical value. So our critical value, again, this is one-tailed. So P T is less than our critical. So let's go to our table and work backwards. We have, in this case, 7 degrees of freedom, and we're still looking for 0.05. So now our critical is 1.895. So therefore, our conclusion, since our test statistic of 2.297 is above the critical value of 1.895, we reject the null hypothesis that the mean is 8.3 in favor of the alternative hypothesis that the mean is above 8.3. Now, the funny thing is, you'll notice that I switched this sign up here. Even if I didn't switch this sign, you still would have rejected. The issue is you would have rejected and concluded it was less than, even though it's very obviously higher. And the reason, and you'll notice the reason why the web work does this is to make you think about your hypotheses. So, even though you get it marked as correct, you would need to notice that this one, even though it will be marked as the correct answer, and is what you should put, still looks goofy. This is why identifying the correct hypotheses is so important, because you can correctly reject the null, but if your alternative is screwed up, then your hypothesis test is screwed up. And just to explain the p-value, in this case, we had 2.297. We got to stay in this row. So that's going to be in between these two. So we can say our p-value is 0.025, or from that, 0.05. And again, we can see because that p-value has to be less than 0.05, we would reject on that basis. So on the exam, you could just list out the p-value being in that range. Are there any questions before I give you the example you'll do on your own? Okay, I'll give you 3 minutes for this one. And if I remember correctly, one of the hypothesis tests on the exam is a t-test. So if you're not working these out, do it on your own. Let me change this to a greater than for you. All right, I'll give you 3 minutes. So at 13, we'll go over the answers. All right, does anyone need more time? Anyone over Zoom need more time? Okay, let's go over it. So first we got to get our hypotheses. In this case, our null is that our mean is 8. Our alternative is that our mean is greater than 8. Our degrees of freedom is n minus 1, so 7 minus 1, so 6. Okay. So our test statistic is 8.3 minus 8 over our sample standard deviation of 1.33 over the square root of 7. Let's put that into our calculator. Oh, 8.3 minus 8. So we get a t-score of 0.597. You can already tell we're not going to be rejecting this one. So now we need our critical value. Since this is one-tailed, we should have 0.05 is equal P, T is less than critical. Did I put T up here? Yes, I did. So in this case, this critical value, we have 6 degrees of freedom, and our alpha is 0.05. So our critical value is 1.943. And so therefore our conclusion, because our test statistic of 0.597 is well below the critical value, or you can say cutoff value, that works too. I'm fine with either, 1.943. we fail to reject the null hypothesis that our mean is 8. And just to show the p-value approach again, in this case, we have 0.597. That's 0.906, and technically that would be 0. So we know that our p-value is higher than 0.2. That is a horrible p-value, which means we came nowhere close to rejecting. So if you wanted to, you could say that. And again, we can see that that possible p-value is nowhere close to 0.05, so we wouldn't reject. Now, all of these were one-tailed because one-tailed is generally harder, but just for the sake of doing two-tailed, here's the only thing that changes. The only thing that changes, so if it was two-tailed, we would have to divide this 0.05 by 2. So we'd have 0.025 is equal to p, t is less than our critical. So in this case, we now have 0.025. So we'd have 2.447, and our p-value would still be above 0.2. That's the only thing that changes. Now, as a practical matter, if our p-value was, say, or if our t-score was, say, 1.5, this doesn't change the p-value. Besides doubling, you still have to double. So for example, in this case, since we have to double the p-value, we would say that 0.4 is less than the p-value. And the reason why is because we'd have to double that 0.2. All right, are there any questions about this or anything about one sample hypothesis tests? All right. If not, then we are done for today. We finish early. And enjoy the rest of your evening.